So, dear students, we are going to see the next session, term to be as motivational part 1. So, the session outcomes are what is quantum computer, about its invention, representation of data qubits, superpositions, data retrieval, entanglement, operation on qubits, and quantum gates. A quantum computer is a machine that performs calculations based on the laws of quantum mechanics, which is the behavior of particles at the subatomic level. That is termed as quantum computer. So, introduction. I think we can safely say that nobody understands quantum mechanics, which is stated by Feynman, a philosopher. So in 1982, he proposed the idea of creating machines based on the laws of quantum mechanics instead of laws of classical physics. So in 1985, Dutch developed the quantum turning machine, showing that quantum circuits are universal. In 94, Peter came up with quantum algorithm to factor very large number in phenomenal time. In 97, Grover developed a quantum search algorithm with this complexity. So representation of data in terms of qubits, a physical implementation of a qubit would use two energy levels of an atom, an excited state representing 1 and a ground state representing 0. So excited state is the outer circumference and ground state is extreme outer circumference. So you are going to hold some sort of core functionality termed to be as nucleus. So the light pulse termed to be as frequency is going to make a traversal over the circle. So your electron is going to transit one state of your qubit to another state. This kind of representation reveals how your qubits is going to be present for your reader. So superposition is another state which is a forced state, which is denoted by tau of 0 and tau of 1. These are two complex numbers. A qubit in superposition is in both the states at the same time. So we can state that according to this depiction, so your light pulse of frequency is going to have half time interval for one side and half time interval for another side. So in some times, for some reader, the qubit will be visible as tau 0. For some reader, it will be visible as tau 1. So the state is not can't able to be tagged, so it is called to be a superposition state. So next technique is termed to be as data retrieval. In general, an n qubit register can represent the numbers through 2 power n minus 1 simultaneously. This sounds too good to be true, is it? If we attempt to retrieve the values represented within the superposition randomly collapses to represent just one of the original values. In probabilistic sense, either it is going to reveal tau 0 or either it is going to reveal tau 1, where n is the number of qubits. So whenever we are intent to retrieve the data, we should have more concentration of negativity term to be as randomness. So relationship among data, which is called to be as an entanglement. So it is the ability of quantum systems to exhibit correlations between states within the superposition. Imagine two qubits, each in the state of tau 1 and tau 0, which has to be summed up to reveal the superposition of bit either 0 or 1 or half 0 or half 1. We can entangle the two qubits in such a way that measurement of one qubit is always correlated to the measurement of another qubit. Operations on qubit is related morely to digital gates. Due to the nature of quantum physics, the destruction of information in a gate will cause heat to be evaluated, which can destroy the superposition of states. So first in qubit, AND is going to play a major role. In AND gate, probably we will be having basically two sort of input in terms of 0 and 1. So which is going to hold the value of n to be is 2. So 2 to the power of n is equal to 4. So quantum gates are similar to classical bits but do not have degenerate output, that is Original input state can be derived from the output state. Uniquely, they must be reversible. This means that deterministic computations can be performed on quantum computer only if it is reversible. Luckily, it has been shown as deterministic computation by Charles. Quantum gates. Hadamard gate is one of the gate which is simplest form of gate which involves one qubit, and it is called Hadamard gate, also known as square root of NOT gate, used to put qubits into superposition. State 0 which is going to throw state 1. Hadamard gate is two Hadamard gates which is used in succession, can be used as a NOT gate. So it is going to reveal the reverse answers. So Hadamard is a philosopher who has thrown such information revealing the state which is representing square root of NOT gate. So controlled NOT gate. So till now we have seen AND gate and NOT gate, plainly NOT gate, which is called as Hadamard gate. A gate which operates on two qubits is called controlled NOT gate. Otherwise, we can call it a CN gate. If the bit on the control line is 1, the invert is on the target line. So this CN gate has a similar behavior to XOR gate, exclusive OR, with some extra information to make it is reversible. So target and control lines are different. The truth table is depicted in the PPT. So 0 0 is 0 0, 0 1 is 1 1. So 1 0 is 1 0, 1 1 is 0 1. So which is reversed. So inputs are controlled and it is thrown to the target line. So example operations, we can build a reversible logic circuit to calculate the multiplication by 2 using CN gates arranged in the following manner, which is going to reveal the carry bits and ones bits. So here carry bit and ones bit. Carry bit and ones bit. So here in this particular depiction, you are going to have two sort of input in terms of 0 0, which is going to again reveal 0 0, and 0 1, which is going to reveal 1 0. So when Hadamard gate has some sort of fitting in the input line, so it is going to reveal the controlled NOT gate, which is going to reveal three sort of inputs, two control lines and one target lines, which is called to be as a CCN gate. If a gate operates on 3 qubits, it is called as CCN gates. If the bits on both the control line is 1, then the target is inverted. So by using that logic, we can read the truth table. 000 is going to reveal the 000. 001 is going to reveal 001, and 010 is going to reveal 010. 011 is going to reveal 111. So if two control lines is 1, so you are going to get the target as inverted. So this is termed to be a CCN gate. So universal quantum computer, CCN gate has been shown to be a universal reversible logic gate, as it can be used as an NAND gate. When our target is 1, our target output is a result of NAND of BC. So this is a truth table. So here in this PPT, we have literally studied about superposition state, entanglement, and we have seen a simple basic AND gate, XOR gate, controlled gate, controlled gate with 3 qubits, and we have seen uh, universal quantum gates. Thank you for this first part of quantum gates introduction. Thank you, learners.